Amelia, we are live now. So you can.
Okay.
Philip is here and we are live.
Okay. Good morning, everybody. This morning, I received the strangest of messages, and that was happy half year. That means we are so glad to have finished off with half of the year 2020s, with clouds of locusts looming over us, and the monsoon clouds looming over us, all in the backdrop of COVID-19. We are so happy to be alive, to be healthy. So before we begin this program, I will request Dr. J. Andrew to please lead us in a word of prayer.
Let us pray. Almighty Father, Lord of all wisdom and grace, we thank you for the gift of life and education. We are grateful to you for bringing us together for today's webinar on flood forecasting. Grant your wisdom to the speaker, guide us and enlighten us. Lord, help us to be more responsible and preserve nature for the future generations. Give us wisdom and goodness to share the natural resources with equity and allow all people to have equality lives, quality lives. Let our land have peace and be relieved from calamities. Bless the patrons, organizers, speakers, and all the participants of this program. Bless St. John's College and make it a beacon of light to this nation. Thank you for hearing us. In the name of Jesus, we pray. Amen.
Thank you, Dr. Andrew. Respected Vice Chancellor. Hello.
Please mute yourself.
Respected Principal Professor S.P. Singh of St. John's College, Agra. Resource person, Dr. Philip Mutulu, Head of Department of Geography and Chairperson of the webinar series, Dr. P.A. Majid. All the co-conveners, Dr. Vidhu Grace, Dr. Rohan D'Souza, Dr. Shalomin Masih, Dr. Preeti Masih, Dr. Mahima Habel, and Mrs. Barkha Baines Single. A very good morning to you all. Today's topic is flood forecasting, and we have Dr. Philip Mutulu to give us a talk on the same subject. Now, flood forecasting, I feel, is the right topic to discuss at this very hour of the year and the time of the year, as several parts of North, East, and Eastern India are experiencing a flood-like situation, as multiple weather stations in Assam, Sikkim, Meghalaya, Bihar, and sub-Himalayan West Bengal have reported extremely heavy rains, that is above 20 centimeters in the last 2 to 3 days. According to officials from the IMD, the eastern end of the monsoon trough continues to run along the Himalayan foothills with the convergence of strong southerly and southwesterly winds from the Bay of Bengal over Northeast and East India. This is likely to lead to heavy and widespread rain in many parts of Northeast India in the next 4 or 5 days. Assam is reporting floods. Bihar is also in a flood-like situation. Cherrapunji, which is known to receive a lot of rain at this time, has reported as much as 50 to 55 centimeters in a day. This pattern of continuous heavy rain will gradually reduce from today till July 2nd. Rains will increase over central India, and from July 5th, we can expect rains to resume over northwest India. And when the rains will resume, we have to be prepared for floods, and for this, flood forecasting is very important. So now I will request our principal, Professor S.P. Singh, to say a few words. Sir.
The resource person of the day, Dr. Philip Mutulu, convener of the program, Dr. Neelia Chauhan, Dr. J. Andrew, uh, and various co-conveners of the program, and dear participants. It is indeed a delight to be part of this program on flood forecasting. Earlier, we had another webinar in which Dr. Philip was the resource person, and we were thoroughly enriched by his wonderful presentation and a lot of ideas he provided us on the process of flood mitigation. And today we expectantly look forward to this conversation, his talk or deliberation on flood forecasting. And on behalf of St. John's College, I extend the resource person and everyone a very hearty welcome and wish everyone a very enriching and meaningful time. Thank you.
Thank you, sir. And your encouragement, your support, and your constant help is the power behind all that we can do. Thank you so much, sir. Now I will call Dr. P.A. Majid to please welcome the keynote speaker for the day. Dr. P.A. Majid. Can we connect to Dr. P.A. Majid, please?
Dr. Majid is not here, so probably you could do.
Please unmute yourself. Majid sir, please unmute yourself.
Dr. P.A. Majid, is he there?
Yeah, I don't think he's there.
He seems to be there, but I think he's on mute. Just a moment.
I can't see him.
Majid sir, please unmute yourself.
Majid sir has not connected today, I think. Monsoons and network connections.
No, he is connected, but there is some problem in his.
Hello.
Okay,
Good morning.
Yes, yes.
Yeah, we can hear you, sir. Yes. He's muted again.
Hello.
Yes, sir.
Good morning, everybody.
Good morning, sir.
Good morning, sir.
Good morning. And thank you, Ma'am Neelia, Madam, to giving me chance to tell something about
Dr. Majid, we can't hear you.
Ajit has got muted again.
So, can you hear me?
Yes, now we can. Yes.
Good morning to everybody. And thank you, Neelia madam. Hello. Hello.
Yes, we can hear you now, sir, very clearly.
Dr. Philip Mutulu is a principal hydrologist with more than 20 years of combined experience consulting and teaching in the area of flood mitigation, flood forecasting, climatic change assessment, and modeling. His notable previous roles include the position of Director of Flood Forecasting 2010 to 2013, coordination and response for the province of Manitoba, Canada. This role entailed providing technical guidance and leadership in land subdivision and flood protection zoning, operation of flood control structures, flood warning, flood response, coordination, and working within various stakeholders and assume optimum flood preparedness structure were in place at the right time. In 2011, Dr. Philip led the province of Manitoba in preparedness and effective response to one of the worst flood in the province's history. Dr. Philip has been an active member of the Canadian Prairies Regional Adaptation Cooperative Program, PRAC, which has a mandate to improve the resilience of the prairies region to a changing climate through collaborative activities, advancing adaptation and decision making. In his previous role at Stantec Consulting, Philip conducted several stormwater design studies for different municipalities, including the city of Calgary. He has also contributed to several major flood-related projects in Canada. Dr. Philip has recently completed a study on modeling flood sensitivity to climate change in a medium-sized watershed with a focus on the upper Red Deer Basin. He has been conducting research in flood stimulation for a changing climate for the Upper Elbow River Basin under the sponsorship of Climb Enviro Solution Limited. He is a member of National Disaster Mitigation Program, NDMP, Technical Working Group on Flood Mapping, whose primary function is to support the implementation of the National Disaster Mitigation Program, NDMP, and has the mandate to develop national guidelines and best practices to meet the national requirements for flood risk assessment and flood mapping and monitoring. On my own behalf and behalf of entire geography department, I welcome Sir Dr. Philip Mutulu in our midst this morning. And now I'll request him to tell something about the forecasting of flood to save lives and to save public property in the same earth. Thank you very much.
Thank you, sir.
Good morning, good evening, good night. Thank you very much for this opportunity. To once
Good
again,
morning, sir.
Good morning, sir. Good morning, sir.
thank you for the opportunity to talk to you once again. This is the second time that I'm making a presentation, and I count it a privilege and an honor to share my thoughts on flood forecasting. So today we shall divide our presentation into 7 components. The first one, I will cover an introduction and provide an objective of the presentation. Then I'll talk briefly on hydrologic cycle, then the causes of floods and types of floods, then spend some time on data analysis, modeling, and forecasting, then coordination and participatory approach, and some future trends, and then I'll conclude. You bear with me because I'm going to be repeating some of the slides that I showed last time, though there will not be many, but I think they will help us in some sections to clarify the presentation. Hello?
Yes, sir. Yes.
I will start with a quote from the scriptures which say, "A prudent person foresees danger and takes precautions. The simpleton goes blindly on and suffers the consequences." Proverbs chapter 22, verse 3. Isn't that a challenge to a forecaster? A forecaster is supposed to foresee the danger with the knowledge that has been provided to him by the Almighty. So flood forecasting integrates a broad range of knowledge, including physics, mathematics, engineering, geography, economics, social considerations, among others. The objective of this presentation is to provide key basic information on the subject of flood forecasting. The presentation presents an overview of forecasting methods while avoiding theoretical treatment of complex flood forecasting tools such as hydrologic models. So I'll try to avoid all the mathematical complications. I don't think they would help us today, and there's not much time for that. We will focus on the past and the present and future of flood forecasting, and also look at a broad view of future trends, including climate change, the use of drones, and community participation in flood forecasting. So you'll excuse me once again. I'll be talking about climate change, but today in the context of flood forecasting. So as an introduction, I'm going to just run quickly through some of the recent extreme flood events. Probably for you people in India, of course, this is a frequent threat. And so I'll just provide examples from North America, just kind of to drive a conviction in your hearts as we discuss this topic today, and see yourself as a person who needs to have a part to play in preparedness. It's a global threat, Almost every week we are hearing flood episodes and flood events happening all across the globe. And they seem to be more frequent and more extreme, like we discussed last time, potentially due to climate change. So one of the recent flooding happened in Australia. It's a very recent occurrence in memory. And this happened in February early this year. What you see on the right-hand side there is a graph just to show the extremity of the event. You can see the month of February actually received more than half, actually more than twice the normal rain that they get during that time. And these patterns are repeated over and over again in diverse places where in a day you get a total rainfall of 6 months, 3 months, and so they are pretty extreme. And this is just an example from Australia because it's fresh in our memories. What happened that time? We had nearly 500 millimeters in some places in Australia, while actually the month of February is less than 150 millimeters. The chart there that I'm showing there is just to show that the return period of that event for 24-hour duration was somewhere between 50 years and 100 years. The other recent example from North America was Harvey. I particularly wanted just to talk about this a little bit because it was very extreme, with total damages of $125 billion plus several deaths. And Harvey actually had a lot of water. You can imagine that there were 14 to 15 trillions of gallons of water that came out of that hurricane. It was category 4. Compared to Katrina, which caused a lot of deaths earlier on in 2005, Harvey happened in 2017, by the way, for those that may have forgotten. Katrina happened in 2005, and incidentally, although it caused more death, actually the amount of water produced by that hurricane was 6.5 trillion gallons. So that was also quite huge, but not as much as Harvey. Katrina was category 5 and Harvey was category 4. So these are recent systems, and in India, of course, you have to deal with tropical cyclones. By the way, in North America, they call them hurricanes. India, they call them tropical cyclones. I think in China, they are typhoons. And in Australia, they are willy-willy. So it depends on where you come from. On the left-hand side, I just provided a 3-dimensional figure of what a hurricane looks like. You can look at the details much later. It's a whole representation of a thermodynamic system, like an engine of a car. And then these are examples that I provided last time that I was making a presentation close to home here in Canada, where we have also seen extreme flood events in one of the provinces in 2013, and then where I used to work as a flood forecaster in 2011 in Manitoba, where we saw damages due to flooding of close to 1 billion, and about 3,006 people were displaced from their homes. And up to today, actually, they are still being settled. They have not completely recovered from that flood. So These flooding episodes can be very devastating, and the effect can last for a long time in many ways. And the effects can be physical, infrastructural, can be emotional, different types of effects. And then that's a chart again I showed for India that I pulled out of the Times of India, where they made a summary of some of the recent flood damages. You can see that quite a number of casualties, especially in 2017 and 18, there were 2,494. And we have a responsibility to make sure that we are prepared and that our forecasting systems are working well, so that whoever needs to be evacuated, whoever needs to move to a different place, or whichever place flood control structures need to be operated, they need to be operated in timely manner. And these operations and evacuations can only happen, if we have proper forecasting techniques. And before I go into more details, I want to recap hydrologic cycle, which is a very well-known cycle to most of you, especially coming from geography background, because this is a basic knowledge of the water cycle that provides the knowledge that we need to have to be able to build forecasting tools and to be able to apply them. So all the building starts from an understanding of hydrologic cycle, and it could be a global hydrologic cycle or just a cycle that is locally based in a local catchment or watershed. That's some good picture there of a water cycle. And as a summary, water circulates in the hydrosphere through a variety of complex paths to form the hydrologic cycle. The global cycle can be divided into three components. The first one is the atmospheric water system, which constitutes the process of precipitation or rainfall, evaporation, interception, and transpiration. The second component is the surface water system, comprising overland flow, surface runoff, and runoff into streams, lakes, and the ocean. And the third one is a subsurface water system consisting of infiltration and groundwater flow and seepage as well. And a good understanding and quantification of these three components is very critical in building an effective flood forecasting system. So recap again of something that we talked last time. I just go through this quickly. What causes floods? And we saw that first, what is a flood? Typically, it's an overflow of or inundation of water from a river or other body of water which causes or threatens loss of life and property and environmental damage. It is normally an overflow of water onto normally dry land. Usually, the inundation of a typically dry area caused by rising water in an existing waterway, such as a river, stream, sea, storm surges, or drainage ditch. Many of these floodings are characterized by overbank flooding or of the waterway. However, flash floods, on the other hand, are caused by heavy or excessive rainfall in a short period of time, generally less than 6 hours, and are usually characterized by raging torrents after heavy rains that rip through riverbeds, urban streets, or mountain canyons, sweeping everything before them. They can occur within minutes or a few hours of excessive rainfall. Sometimes a flood event does not necessarily imply that a river has burst its banks or caused damage, but denotes an event that exceeds a defined threshold level. Probably an example in that line is sometimes when you have elevated groundwater levels that intersect with ground surface, you can actually have flooding in an area. And so this flooding is not necessarily coming from a river. Even also flash flooding also does not emanate from a river channel. So it's important to understand that flooding does not necessarily have to emanate from a river system. It could also be a tide from a lake or from the ocean. In terms of flood forecasting, there are a few basic components that one needs to understand, because these components are the things that you provide to the consumer of a flood forecast in order that they can prepare adequately. And therefore, a flood event is characterized by the peak flow rate, time of peak flow, flood elevation, volume, duration, and timing. These parameters can be inferred from a flood hydrograph, which is the time distribution of flow and are important when providing flood forecasts. This is a pictorial presentation of the above statement. This is just a graph of time distribution against the vertical axis, the flow rate or volume or water level, whatever parameter you're looking at. And one of the important things is peak flow. We want to know the maximum volume that we're going to get, so that if we are preparing a reservoir to receive water or to release water, then we know how we are going to operate that reservoir or floodway. Or if we know that the flooding is going to encroach a wide area in the floodplain and probably affect people, then we can evacuate people that are within the close to the flood zones. So the peak flow is very important in determining the maximum amount of flow. And also the time of rise, that is the time between when the flood starts and the peak time, is very important in terms of timing, so that you can provide the evacuation, or the emergency manager should know this so that they can know they have enough time to evacuate, or the operators of flood control systems, they have enough time to operate their water flow, water control structure, so that they are not overwhelmed by flood when it comes to the peak flow. And right there on the bottom there, on the horizontal axis, you also have the flood duration. We also want to know how long this flood is going to last, so that we can have a good picture of how we are going to operate our flood control systems, or how long we are going maybe to keep people away from the flooded zones. So typically, a flood forecast should be able to provide those components of a flood event. So I think that's a kind of a recap, a repeat again, but I just want to focus on the second portion of that slide. What causes severity of flooding? Because I think this is very important. And these factors, actually, they need to be taken into account by our flood models. They need to be able to take into account possibility of extreme rainfall, temperature, preceding high soil moisture conditions, antecedent high river lake levels, with chill conditions that produce fragile ice, like in Canada. Maybe you may not have that problem in India, but probably near the mountains, you could have this problem of fragile ice. Then, of course, our forecasting tool should also be able to factor in climate change. And then land use practices needs also to be accounted for, and land slopes as well. How these characteristics, how these patterns are formed, or the way they are, will encourage or discourage extreme flooding episodes. So that was kind of introductory. Now I want to go and just talk a little bit about data analysis, modeling, and forecasting. Sometimes the difference between data analysis and modeling may not be very distinct, because modeling is a kind of analysis, but it's a specialized type of analysis. So analysis is more general, but modeling is a specific component of data analysis. So we are now into the realm of forecasting, but I wanted to kind of reiterate what the mission of Flood Forecasting Center is. I have looked at the Indian mission and what their centers are focused on. Some of these are captured in this mission, which is from Canada. And typically, a Flood Focus Center provides strong science-based hydrologic forecasting, flood warning, and hydrologic reporting to all levels of the government, private sector, and public. Actually, at this point, I need to mention that in some places, forecasting for flood is done together with the weather forecasting agency as well. In Canada, they seem to be separated. So our flood forecasting center is here, separate entities, although they link up with the meteorological centers who provide data to them. But if you look at a place like Australia, actually you have Weather Bureau, which actually houses the flood forecasting or hydrologic forecasting. So this arrangement varies from one nation or state to the other. I think similarly in India as well. So the main task of a flood forecasting center should include the following: giving direction to emergency response, facilitating optimum operation of water control works such as dams, diversions, and floodways for flood damage reduction, conducting hydrologic, hydraulic analysis using state-of-the-art models for flood forecasting and flood damage reduction, studies and to assess impacts of infrastructure changes such as road and bridge replacement, modeling research and development, conducting dam operations for flood control and to ensure a sufficient supply of water in reservoirs and rivers and suitable lake levels for recreation and fish, promoting long-term flood damage reduction by ensuring that developments and subdivisions permits and crown land sales adhere to provincial or state land use policies regarding the risk of flooding and erosion, operating a provincial hydro network or state hydro network of water level and storm gauges, and provides hydrometric data in near real time for multiple use, contribute hydroclimatic information for the design of water control structure. So it's quite an integrated responsibility for a forecasting center. They don't just provide forecast, but they provide customized information to different consumers. Of course, all these consumers, this data is a form of a flood, but it's a different process type of flood. Like you're not going to provide the same data to an engineer like the data that you're going to provide to a public person or to the communities that need to evacuate. So the data must be, the information must be tailored to the need of the consumer. And there are different types of typical flood products depending on where you come from, whether you come from North America, Canada, or India. These products change with time, and sometimes they are driven by stakeholders. You know, they would come and say, yo, we need this type of flood, we need to prepare our farms, so can you provide a weekly forecast for, you know, soil moisture, which is a part of flood forecasting. So they are all different types, and in a typical flood forecasting center, you find precipitation maps being prepared on a frequent basis, soil moisture maps, snow water equivalent maps, like in Canada where we have problems of snow. They issue timely flood alerts, watches, advisories, and warnings, providing daily flood report summaries, weekly flow volumes, levels, forecasting river flows, lake levels, reservoir levels, daily, weak ocean tides and wave action, wind setup, wind alerts on major lakes, and so on. So I'm just trying to show you the wide responsibility that a flood forecast center has. It's a lot of data products that are needed. And with that introductory for what happens in a forecasting center, let us just go now into forecasting tools. In a forecasting tool, you need data, of course. And this data comes from diverse places. Could be from weather stations, from satellites, from weather radars, from automatic river gauges, from spatial graphs, soil moisture, snow depth, water levels, and now more modern flood forecasting systems are also using data from numerical weather prediction models and also drones. I'll briefly talk about the drones towards the end of the presentation. So it's a huge amount of data, and the thing that I would like to underscore here is the need for the governments to invest adequately to have monitoring stations that are sufficient to provide data that is required to give accurate forecast. Yes? Once you have that data, what do you do with it? You have to put it somewhere so that you can provide a forecast. But I want, just before we go there, let me just expose ourselves to some of the challenges in forecasting. Like some of you that are where maybe, I don't know whether any of you has been involved in weather forecasting. I was a weather forecaster before I became a flood forecaster, so I have backgrounds in both meteorology and flood. The occurrence of extreme hydroclimatic phenomena are complex and chaotic with random and deterministic components. Flood forecasting faces challenges of complex uncertainties from a variety of sources, such as chaotic random nature of the atmosphere, land, ocean processes. The chaotic phenomena is often caused by incomplete knowledge of the system, including initial conditions. Errors in the initial conditions can grow with time to make long-term prediction unreliable, even for a deterministic system. We shall see what a deterministic system is, shortly. A phenomena called the butterfly effect. I guess some of you, most likely you've heard of the butterfly effect. Although the application of chaos theory remains mainly in the realm of research, literature is replete with discussions of the subject. For those that are interested, you can search on the internet. And the treatment of chaotic systems requires very huge computer power. But I think now with the emergence of powerful computer, significant advances in the area of chaos theory are being made. If you heard the story of butterfly, somebody said that a butterfly just flapping its wing, you know, the effect might seem small, but that effect can grow and have an impact somewhere very far away. That's called the butterfly effect. And this effect usually is problematic in weather and flood forecasting, because it means that if the initial conditions of your system are not well known, then you will not be able to forecast your rainfall or your flood very well, because the error, any perturbation or any disturbance of your initial system is not well captured, and then you'll not be able to do that forecast well. Forecasting weather and flood is both a science and an art. I think I need to say that. The capacity to combine scientific analysis with informed instincts and sound judgment. The science lies in the ability to understand how different atmospheric and hydrologic systems interact to generate floods, and the ability to apply and or customize the right forecasting tools to accurately mimic the evolutions of a given event. The art of forecasting mostly develops with experience, and it includes the ability to make timely and reliable decisions and to choose the best forecasting tool in a given situation. So anyway, what I'm saying that for us or for our agencies to be able to provide good forecasts, they need both the science and the experience. You may have the science, the knowledge, the mathematics, but you will lack the nutrition. Sometimes you'll even find the mathematics don't work at all, and you have to make very quickly decision, and that can only come from experience. So for those of you who are students who are looking to become forecasters, that's something that you'll have to learn along the way. So those are just our offside statement, but these are cautionary statements that I wanted to make right from the beginning. That's just a picture of a butterfly, and the effect is also called Lorentz diagram. If you are, for those that are interested, you can go and do search. There are books on that theory of chaos in the atmosphere, which translates to chaotic processes in flood forecasting, because you cannot separate floods from the atmosphere. Without the atmosphere, then there are no floods. So whatever errors or whatever disturbances occur in the atmosphere during a flood event, they will be propagated in your forecast system. Anyway, that's a bit aside, but it's a very interesting subject. It's a very complex subject, but some of you might want to explore that. So how do you treat these complex systems in flood forecasting? Hydrologic systems are generally complex, and physical laws that describe natural hydrologic phenomena are difficult to formulate. Thus, a recourse to hydrologic models is made, whereby hydrologic systems are represented by a set of simplified mathematical equations. A hydrologic or flood model has three basic components. The first component is the input, for instance, the rainfall. Then right in the middle, you have the processing system, which is called a watershed. So it's like the system, the watershed system takes in input, and then it processes that input and translates that input into output. That processing or that procedure of transformation is represented by a mathematical, can be represented by a mathematical model. So you have input, then the watershed, and the output, just to simplify. Hydrologic systems are often treated depending on availability and quality of data and objective of a given study in various degrees of complexity, from deterministic to purely stochastic. Stochastic, another word for stochastic is probability or statistics, if you want to sound simple, but they prefer to use the word stochastic in floods and hydrology. This includes simple linear empirical to highly complex statistical methods. Some of the linear methods that you can use to forecast a flood from rainfall is building a simple linear regression equation. But then, because these hydrologic systems are not linear, you will find that your regression equation doesn't give a good forecast. So you want to go for something complex that describes what is happening in a hydrologic system. So secondly, we have deterministic, which are also called process-based models. And these are able to account for biophysical processes that are responsible for generating runoff from precipitation. Then you have lumped type of models. And these are type of models that do not consider spatial variability. For those of you that are experts in GIS, you know how important it is to model spatial variabilities in processes in an environment. And therefore, this lumped model does not account for that variability. But very interesting thing is that some of these lumped models can even work better than some of the physically based models in some cases. Yeah, that's what we found when we are forecasting. And so that's why I brought it up there. It could be simple. It does not account for the spatial variability, but during extreme flood events, sometimes you find that they work actually pretty good. Then this distributed modeling, that is where you can account for variability, spatial variability in soil, vegetation, land use, and so on. Then you also have event-based or continuous. Event is something like that happens like a short-lasting storm which lasts only for 6 hours or 24 hours, and some of these intense events are actually responsible for very heavy flash flooding and so on. And so when you build a model, you want to know whether your model is going to be forecasting just events like those ones, extreme events, or it is a continuous system. A continuous one will track moisture for a long time over the years, throughout the year, and then when the rains are about to come, it will already be knowing what was the moisture in the soil 3 months ago, and therefore when the rain comes, it is able to forecast what the flood, what type of flood and the quantity of flood will be generated from that rainfall event. So a forecasting system can be any of those, a combination of the above, and typically it's recommended that you use combined methods. And therefore you find that in forecasting, there's not really a single forecasting technique that works. And that which works better seems to be a combination of any of the above. And sometimes actually when you are doing actual operational forecasting, you find that even your model doesn't work and you have to quickly do some calculations aside, addition and subtraction here and division there and there to come up with with some numbers, because the hydrologic systems are very complex, as we have said, starting from the atmosphere to the ground to the vegetation and so on. Some examples of these tools, there are many forecasting tools, and some of them are available for free, others are proprietary, and so it's upon every government agency to decide what they want. If they want very complex models, they may have to buy it for several thousands of dollars. but still they can also go for free software that is available on the internet for free. And actually, some of these free software are being used very effectively, not only in North America, but in India. Models like HMS, CRAS, and SWAT, they are being used by agencies in North America and India and other places. And these are all free. Others like Mike Flood, Mike She, you have to buy them, but they are expensive. And typically what an agency wants to do is to test different forecasting techniques before they can say this is what works best. 5 years ago, I was involved in a project in Canada here where we evaluated different forecasting methods and rated them, and we submitted that report to the government. And so it's always important, if a nation or a country is going to establish a forecasting system, it is not wise for them to just call a consulting firm to establish a forecast system, because it might not work. What they need first is to evaluate different forecasting schemes and see which one works best. And even if the existing ones do not work, then they need researchers from the university who can help them with research into tools that can be used as complementary methods to help them forecast better. So that's why we need research. You remember I mentioned that one mandate of our forecasting center is to be involved in research for better tools of forecasting. On your right-hand side there, you have one of the models. It's actually a simplified model, but a model like this one, you can see that it represents about 5 layers of the hydrologic system, starting from the vegetation, surface depression, surface zone, percolation, groundwater percolation. All these processes are represented by mathematical equations for those that are familiar with hydrologic models. Currently, what's happening is that there's a push towards integrating what is called hydrologic models and hydraulic models. And that's one of the things that the Mike She and Mike Flood do. In this case, what I showed earlier on, I showed you a HMS model that is really hydrologic, and it deals mainly with the hydrology. But when you want to see how water moves through channels, through pipes, if there are pipes or channels or canals in your system, then you want to use hydraulic models. And therefore, what the push is currently is to couple hydrologic and hydraulics model. So here I've showed an example here, and the hydrologic model provides something like the surface runoff. When it rains, some of the water infiltrates to the ground, some water evaporates. What remains after it fills the ponds on the surface, then some of that water becomes runoff. But then how this water is going to move through channels is modeled using hydraulics. And we can have several layers of this system in a hydraulic model, and these layers are well captured by using GIS system. Dr. Achner, of course, last time presented application of GIS, and so GIS applications are finding very wide applications in flood forecasting. Actually, there's no most of the flood forecasting tools that are being developed today, they have GIS components so that you can be able to integrate different layers of data and then do some mathematical operations between these different layers so that you can come up with your flood forecast. So the first layer could be a layer of rainfall. The second layer could be moisture. The third layer could be land use. And then after that, you have a response equation there. And then the fourth layer is the excess rainfall or runoff. And that layer now is laid into hydraulics layer down there, which routes the flow. So these layers operate on one another using mathematical models. I'm really sure those of you who have interest in GIS, they exactly know what I'm talking about. So these layers can operate upon one another through mathematical equations, which are the models, hydrologic and hydraulic models. So there's push towards distributed coupled hydrologic models coupled with 2D hydraulic models, because that's the only way we can capture the type of floods that we are getting today. We need to see them move in all directions. In fact, now there's a push towards three-dimensional models where you can be able to simulate the vertical motion of floods. But basically what is working out today is the two-dimensional, where you have the X, Y, Z, X, Y directions. Now, when you are doing forecasting, there's something very important in this. Because of the chaotic nature or random nature of the atmosphere and the hydrologic systems, you are not just going to give a single number. You need to tell the people who are receiving the forecast, yeah, this is my forecast. But because there are a lot of uncertainties because of data, because of incomplete knowledge of the system, I think my range of focus should lie in this, between these 2 points. So you give an upper range, the middle range, and then the lower range. And typically that helps prepare the emergency preparedness people know how to prepare for the worst conditions, because you've told them the upper possible number of the flood volume that you can see. And so when you are forecasting, be aware that you need to provide information that will help people prepare for the worst. You know, even if the worst does not happen, at least you are prepared. It's better that it doesn't happen, but if it happens, then you are going to be in danger. And that's where sometimes the meteorologists and the flood forecast find themselves in danger, because they forecast something high, and then people are evacuated, but nothing happens. But you see, the long-term gain is usually worth it. Always provide the largest number.
Oh, partner.
So it's vital to provide margins of uncertainties in flood forecasting in order to help emergency managers and other stakeholders prepare for the worst scenario of flooding. Now, what you have seen in my presentation in the previous slides is a lot of information that goes into forecasting tool. So diverse information also means different groups of people that would be involved in providing this information or processing this information or consuming the flood forecast. And that's where there's a need for very strict coordination and participatory approach. This is a type of approaches that are becoming more popular, where forecasting agencies are now involving the communities in their forecasting systems. And I think one of the best forecasting systems, especially for flash flooding, is in India, where they involve the local communities. Sometimes it involves even sending information about how is the river behaving in that local area, how is it, you send that information. It is so integrated in forecasting system. So this chart here will differ from different agencies, but it does just show the linkages or synergies between a flood forecasting center, different government sectors or departments because you cannot forecast there as an entity, you really need to know what people need out there. And as they give you feedback, then you know exactly, you can tailor your information so that it is most useful to them. So you cannot work in isolation as a forecaster. You need to, there's a need for participation of different agencies. And then during when there's a flood event, one of the things that happens is that there are frequent meetings of different stakeholders, consultants, emergency measures, forecasters, and so on. And that's something also that is popular in India. And all these people discuss as the flood event happens, the forecaster will provide what is it that you are forecasting. Okay, where are we going to need to evacuate people? Where do we need to operate our water control structures? And therefore, this is a picture where you might see me somewhere there, but it's a picture in our the flood forecasting center that I used to head. Every morning at 8:30, we used to have consultative meetings. And at that time, there was a heavy flood, and houses and properties were being washed away. And it was very important that we consult one another and make the best decision for that day and provide the information in a timely manner. And therefore, it's almost overwhelming. This is not a job that a forecaster can do alone. He'll have to rely on other people to be able to provide the best product that can be consumed by the people outside there. So, as a recap, we have seen the need for data monitoring, investment that is required from the government, the need to combine this data into models, the need to build models or to test models specific for every area, the need to collaborate with one another, with different agencies so that you provide the right information in a timely manner to the people that need the information most. Now, looking into the future, a lot of information is now available, especially from different sensors that are being sent into the atmosphere, whether these are satellite-based or radar or the drone. And there's even a science or a specialty that is emerging of data, big data branch of education. I think they're already offering that in universities. So data assimilation, and I just put a drone there because it's become so popular, and recently it is being used in flooding, not only in mapping. I mean, it is also providing forecast in some areas. But so I think I need to, moving to the future, the drone is going to be an aircraft that will become popular in flood forecasting, because the good thing, it can be localized. There are a lot of drones all around the globe, and they can coordinate information with one another. They can receive information from the forecast center, send pictures to forecast centers, and so on. Anyway, real-time data has become more readily available from automated Earth-based sensors, e.g. soil moisture probes, hydrometric, weather station, and so on, and air-based platforms, for instance, drones, radar, satellites, etc. Flood prediction models can be built to take advantage of such information by including data assimilation. That is called adaptive forecasting technology. The technology can automatically ingest real-time data as they become available in order to improve forecast. So the technology that is being developed now for forecasting is to be able to be adaptive. The model can ingest data from the drone or from the radar directly. And then as it gets that data, it updates itself and improves the forecast. The second paragraph there says, apart from the data assimilation capacity, adaptive models can be designed to use feedback mechanism where errors in previous predictions are utilized to improve future forecasts. In addition, model parameters can also be allowed to change with time during the simulation period, a process particularly attractive when parameters are sensitive to environmental variabilities. This way, uncertainties can be accounted for. In particular, environmental prediction models with automated adaptive features can be very useful in flood forecasting, reservoir operations, irrigation scheduling, and other environmental predictive systems. So here I have a system. The drone gives this system new data. So my model will update itself and then improve my future forecast. Just that's simply put. So the model is not a static thing, it can adapt itself, and that's where the future is moving to. And also the other thing that we are moving into future is the integrated technical components in the flood forecast. And this should be, this is a depiction of what a platform, a forecasting platform should look like. Some of them are already into this kind of platforms, and some of the projects in India and North America already taken advantages of this technology, where you are putting different components together, integrating them so that you can seamlessly provide a forecast. So we have a flood forecast model, GIS, database management system, meteorological forecast, post-processors, stakeholder engagement, information review process, flood maps, reports, and so on and so forth. You can look at that diagram at your time, see what type of components we have. The other thing also that they are trying to do is to seamlessly couple numerical weather prediction with flood forecasting models. So what you find is that now the weather forecasting does not work as a separate entity, but what they have done is they have linked their tools directly to the hydrological flood forecasting model, so that the data is streamed directly between the two systems, the numerical weather prediction models and the flood forecasting models. But these are not the only data exchanges that are taking place. The same flood forecasting model is also receiving data from the river level measurements, and also from air-based, airborne satellites, and so on and so forth. So it's an integration of a lot of information. And on that diagram there, you see on the right-hand top, those are supercomputers, because it's not possible to do a forecast of weather or very advanced flood forecasting without those supercomputers. These are systems that are capable of computing trillions of data computation within just a millisecond. These are called supercomputers, and they have actually to be cooled down by cooling system because they are so huge. Now, one of the things is that because of the complexity of flood forecasting, the future is looking at developing very well defined protocols. And these protocols will ensure that nothing is missed out, no information is missed out. There's good synergies, feedback systems within the flood forecasting system. So the paragraph there reads, flood warning and alert systems can be more effective when a participatory approach is put in place, a process where the stakeholders, public, are properly engaged in critical processes during pre-flood preparation and planning, the flood event occurrence, and post-flood programs. As well, during developmental phases of scientific tools, modeling and forecasting, participatory approach can offer insight into flood products' consumer needs. At the minimum, a well-designed participatory approach model consists of synergies, protocols, and feedbacks to ensure cost-effective and maximum flood damage reduction emanating from the system's implementation. So this is what a simplified protocol should look like in a flood forecasting system. So right there on the top left-hand side, you have the flood forecasting center. But now the flood forecasting center is not going to stand alone. It's going to be surrounded by a lot of staff. There will be a detection. Detection involves a system which sends the signals when we need to activate a flood forecast system. And it's related to threshold or critical levels. Also, critical levels involve the calculations of the time when we need to provide a forecast and so on. And so it's a complex system, but one of the things that I wanted to reiterate there, this system includes a response component, recovery, review, performance recommendations, repairs, preparedness, and so on and so forth. It's a system that helps the flood forecaster to improve their system because they are getting feedback from different components from outside of themselves. And that way they are able even to provide information that, again, as I repeat, information that is tailored to the consumer and the right information. And information that is understandable. You don't, when you're providing a forecast, you're not going to start talking about mathematical jargons. You need these protocols, these synergies and feedbacks to let you know, no, you are not providing information that is consumable because you don't understand your mathematics. You need to simplify that information. So all this feedback will help us improve our forecasting system. Again, this is a bit complex diagram, but when you go through it, you later on during your time, you see it will make sense. Now, so what have we seen? The previous slide was about linking different components in a flood forecasting system that will be beneficial and eventually lead to reduced flood damage and proper response, and so on and so forth. Now, the other challenge here is the climate change and flood forecasting. Climate variabilities and change. When I talk of variability, normally these are short-term variabilities. You see, like a diurnal change, that's a variability. Diurnal change or weekly variability of a climate parameter, that is a variability. But a change is something that can be measured in terms of at least 30 years. That's when then you can start talking about change. Climate variabilities and change can trigger changes in hydrologic cycle, land use and cover patterns, leading to potential impacts on magnitudes and flow timing. Climatic processes constitute a major part of hydrologic cycle, and hence the study of climatic variabilities and changes and their potential impact on hydrologic systems cannot be overemphasized. Analysis techniques should adequately anticipate possible impacts of climate variability and change on flood generating processes. That means a flood forecasting tool based on historical data may not be effective with time and needs to be adjusted with time. Something that I would have talked about, but I didn't have time, is a model contains parameters, and these parameters are usually calibrated based on historical data. But if you are going just to use historical data, that model may not work in future if there's a climate change effect in flooding, because the parameters will not reflect that because they are based on historical data. That's why the current models have now to have the capacity to adjust themselves to climate change. And therefore, the models that we are using are kind of constructed to be able to do that, to be able to factor in climate changes. Traditionally, parameters derived from extreme hydrologic statistics were based on assumption that the climate system would be time invariant. A climate system that is time invariant is a system where the mean, for instance, the average conditions do not change with time. But now with climate change, those are going to change, and therefore the system is no longer time invariant, but is now varying with time. It's a non-stationary system. So assumption of stationarity or a time invariant may not hold because of expected potential climate change due to global warming. And so some of the things we are doing here is to look at the models. How do we adjust flood forecasting models if we are expecting temperature to change by this much in the next 30 years? How should we adjust our model? Because, by the way, a flood forecasting model is not just used for short-term forecasting, but they are also being used for long-term forecast so that you can also incorporate that into long-term planning. That's why we need forecasting models that take account of potential climate changes. So after my long story, I want to conclude. And we have looked at the examples of damages that are caused by climate change. We have looked at the hydrologic cycle as basic knowledge that you need to develop your models. We have looked at chaotic nature of models and their uncertainties. We have looked at the need to collaborate between different agencies and the need to lay down protocols for flood forecasting. We have looked at the future. Where are we heading in terms of flood forecasting? And we have also looked at the problem of climate change. In conclusion, I want to thank you for offering me this opportunity. And we see that floods are increasing and becoming a global threat. And flood forecasting needs collaborative effort in sharing knowledge, developing effective forecast tools, and the governments need to invest adequately to build flood forecasting platform. We look forward to further collaboration in matters related to geohazards. So I believe today we have seen flood forecasting is a very wide subject, and sometimes you might have thought it is a very narrow, bounded discipline, but it is not. It is a conglomeration or integration of so many different types of knowledge. And I believe each one of us, you can fit somewhere. You don't have to be that flood forecaster who is going to operate a model, but you can feed, you can help in evaluate ecological factors that affect flood forecasting, geographical factors. You can be involved in GIS and flood forecasting. You can be involved in social factors that affect response to flood forecasting. If you are good in mathematics, then you can help develop and evaluate flood forecasting models and so on and so forth. So it's an area which integrates different knowledge and expertise. So different professionals are useful in forming a part of flood forecasting system. Thank you very much. That's the end of my presentation today.
Thank you, sir. Thank you, sir.
Thank you. Thank you, Dr. Philip. You have touched upon flood forecasting from, you have looked upon it from every detail and have given us a very exhaustive and a detailed view as to the complex task of flood casting. The tech team, can you please put me on the screen? Dr. Mutulu, you picked your objectives from the scriptures. And here in India, as well as globally, when we are facing the locusts, the pandemic, the flood situation, the lightning strikes, it reminds us all that is written in the Bible. You also explained the hydrological cycle for the ones who are not familiar with the subjects of geography and the sciences which teach the hydrological cycle. Plus, and told us about the review of the recent flood situations, especially the floods in Australia, the severity and the frequency of floods, and how conducting data analysis, modeling, and forecasting, and what are the missions of flood forecasting centers. Conducting dam operations and providing maps related to floods, flood casting in both for the science and arts background people, that with informed, along with flood analysis, informed instincts and social judgments can save so many lives and biospheres, with both the combination of arts and science. Now, I will not take too much of time, and we will go straight into the question answers session. Dr. Bob, Mr. Bob, who is the youngest and the most dynamic co-convener from the Department of Geography. If you're present, can you please ask some questions?
Yeah, can you hear me?
Yes.
Yes.
So, good morning, sir. Morning, Philip, sir. I just want to ask 2-3 questions. One is that you are talking about formulating a model for flood modeling, right? So, I have read some studies, and whenever we are considering modeling, flood modeling, and its mitigation, most importantly, then we are also considering social and institutional framework. So right now, the models you showed us, those were on a very quantitative, had a very quantitative aspect to it. So do you think weightage should be given to social and institutional factors also when we are talking about mitigation?
Yeah. Perhaps then you are familiar with conceptual approach to building model. The conceptual approach brings in different expertise, and then
Yes, sir.
Can
We
you
can
put
hear
your
you.
mic on, please? Can you mute your mics?
Participants, please mute your mics.
So now I request to Philip sir, please unmute your mic.
Sir, you are muted. You have to unmute yourself. Philip, sir, you are muted.
So am I good now?
Yes, yes,
Yes.
yes.
Okay, yeah. What I'm saying is that the approach today is called concept modeling, where you bring groups of different people together, and then every group comes with a component, and these components are put together to form what is a conceptual flood forecasting model. And therefore, this involves sociologists, response health practitioners, mathematicians, economists, and so on. It's a very complex approach, but I think it's an approach that we cannot avoid, because the ultimate goal of flood forecasting and mitigation is to save lives. And we cannot just save lives by mathematics alone and physics. No, we need to know human behavior and response to floods. and
Okay.
how do they conceptualize risk flooding and that kind of stuff. So actually, you find that in the subject of flood risk, there is something called cognitive studies, where you study the behavioral or the behavior of a human being in terms of conceptually, what does he think a flood is? How far can he remember? Does he think a flood is going to happen soon? And using his mind, he can say, I think there's going to be a risk of high flood this year. And why does he think so? Because, in his thinking, it has this already inbuilt cognitive process that can be used to provide a forecast. I remember my grandfather, before he died, he actually used to forecast weather very accurately, I would say. And it would just by observation or from his past experience, even from feelings, his body feelings, he could tell it will rain in 2 months and so on and so forth. So there are a lot of traditional knowledges even that are being incorporated into this model. Indigenous people, in fact, now are becoming a big part and parcel of these systems. They are being invited to conferences to give papers on what is the best way. For instance, do you think we should manage land to be able to avoid flooding? Yeah, so these things are, they are picking up speed every corner. And I said the ultimate goal is to prevent damage, to minimize damage, and to be sure that we are providing specific information to people that need that information. And that information must be provided in a way that those people can understand in simple terms and can effectively apply that information.
Okay. So I had one more question. That when we are talking about the probabilities and when we are talking about predictions, then that means we are going into inferential statistics. So I just want to quickly, if you can just guide me through that, what should be the assessment that we should look upon? Like when we are going for probabilities, what are the percentages we are? I know nowadays it's all done in softwares. We are using SWOT and ArcGIS and all those softwares. It's majorly done in softwares right now. So I just wanted to quickly, if you can just guide me through what should we be looking upon when we are developing statistical probabilities.
There are different things. One way of building a stochastic model is to look at time sequence of rainfall runoff data. And you can look at this time sequence and determine how the mean or standard deviation is changing with time. And you can use the mean and standard deviation as your predictors for future. That's an example of a probabilistic model. Another example of a probabilistic model is looking at the frequency of big events. You can look at data and do analysis to determine this magnitude of flood. When is it again likely to occur in future? And you can factor this information into your flood forecasting model. Your flood forecasting model, the physics one, the physics based will just tell you, oh, I'm using this equation, this physical equation, because I know loss of motion will tell me that the water that comes in, some of it evaporates, another one, some other component infiltrates. What is left is the runoff. So I'm going to use those runoff equations to produce my flood magnitude. So that's what a physically based model will tell you. But the probability models will basically depend on historical data and just calculate parameters like mean, standard deviation, and so on, so that they can forecast for the future. Yeah, if you want, I can send you some references that you can look at.
Sure, sir.
Yeah.
Okay. So I'll contact you regarding that. if I am allowed to ask one more question.
Yes, yes, please go.
Yeah, okay. So we were also talking about land use. So I just want to ask that what are the parameters that we are looking into when we are assessing land use?
Land use, you can look at land use from two perspectives. The first one, land use, can also refer to land cover. So land cover can be a particular type of soil or vegetation. And this type of soil has got some particular infiltration characteristics. While the plants, they have particular characteristics of evapotranspiration. So if you know the type of soil and the type of plant that is in a particular area, then you can use mathematical equations to calculate how much water, for instance, is lost through infiltration through those soils, or how much is evaporated into the atmosphere. Or if the land has been stripped of vegetation and maybe it has been paved with hard tarmac, then no water is going to infiltrate in that area. So almost all the rain that comes onto that area is going to run off, is going to form a flood, apart from little evaporation. But by the way, evaporation is not a very critical factor during floods, because floods happen very quickly. Unless you are looking at long-term soil moisture variations, evaporation does not really matter for short-term forecast. But when you are doing long-term tracking of soil moisture, they do tell us, okay, our soil moisture, because of evaporation, it is experiencing moisture deficit. So if we get amount of rainfall of this amount, then we are not going to get a flood. But if there's a lot of soil moisture already, a lot of moisture in the soil, then you see, if we get this amount of rainfall, we are going to get this amount of flood coming from this type of land use. So land use mainly is infiltration, slope, and cover. And sometimes on long term, it considers evapotranspiration.
Over to you, ma'am.
There is, if Dr. Mutulu will allow, there is time for one more question if anybody has. Dr. Mahima?
Yes, ma'am. Ma'am, I have one question.
Yes, Dr. Vidhu, please.
Yes. Thank you, ma'am. Ma'am, a question has come up that what is the meaning of 100-year flood and how is it used in flood forecasting? A student has asked, what is the meaning of 100-year flood and how is it used in flood forecasting?
Yeah, a 100-year flood, for instance, would mean a flood with a magnitude that on average would occur after every 100 years. But it doesn't mean that if a flood of maybe 500 cubic feet per second occurs today, it will occur again after 100 years. No, it is not. It is not going to mean that. It is an average number of how frequent such a magnitude occurs. But it is mainly used in designing capacities of things like a dam or a culvert. So, for instance, if you want a dam, to design a dam, you'll want that dam to have a life, maybe 500 years. So you would like that dam to be able to have capacity which is sufficient to hold floods that are able to occur during that period of time. So you might want to design your dam to be of 500-year return period, so that a flood that is likely to happen within a span of 500 years will not overwhelm the dam. So this time you are not forecasting. It's a kind of a forecast, yes, but it's a design to size your capacity of your water control structure. So typically, when it comes to forecasting, we don't use return periods, we use the models. But if we are designing any hydraulic structure, then we use return periods because they help us determine the size which is sufficient to hold a flood of a certain magnitude, which has an average occurrence of, for instance, 100 years. Okay?
Thank you, sir. Thank you so much. Over to you, ma'am.
Thank you, Dr. Mutulu, for taking all the questions and explaining them in detail, even at this late hour in your country. And now I will request Dr. Rohan D'Souza, Associate Professor from the Department of Botany, to say the vote of thanks.
Thank you, ma'am.
Dr. Rohan D'Souza.
Yeah, thank you, ma'am. I hope I'm audible. Hello, am I audible?
Yeah.
Yes, you are.
You are audible. Sure. Thank you, ma'am. Respected Dr. Philip Mutulu, our resource person for today, Professor S.P. Singh, our principal, Dr. P.A. Majid, the chairperson, Dr. Neelia Chauhan, the convener, all our co-conveners, and of course the participants. A very good morning to you. All good things come to an end, and so has this webinar. And now it's a privilege to propose a formal vote of thanks to such an elite panel of academicians today. At the onset, we all give glory and honor to Almighty God for his many blessings and for keeping us all safe in these precarious times. And this has indeed been a most informative session, sir. I'm sure Dr. Philip's wonderful slides and lucid presentation have reached one and all, irrespective of their fields of work, irrespective of their grasp of the subject. We are happy to have him with us again. He was with us about a fortnight ago where he talked about flood mitigation. And floods, yes, they have indeed been a calamitous proposition for mankind since ancient times, and they find mention in almost all our historic texts, including the Bible. And I, for one, was totally engrossed in this presentation. On behalf of St. John's College, sir, I take this opportunity to thank you for accepting our invitation and for being connected with us at what must be quite a late hour in Alberta. I suppose it must be almost midnight for you over there. Thank you. We are deeply indebted to our principal, Professor S.P. Singh, who always has time for us, however packed his schedule. Sir is a constant source of motivation. Moving on, any event of such proportions can, of course, not be the work of a single pair of hands. We need the cooperation of many minds, many hands behind the scene. And a heartfelt thanks goes out to our chairperson, Dr. P.A. Majid, head of the geography department, and our convener, Dr. Neelia Chauhan, and associate professor in the geography department, for being at the helm during this entire webinar series. They've been up at all hours, incessantly sharing, collaborating, planning, executing. And to all our co-conveners for their tireless efforts and diligence that have made this webinar successful, a big thank you goes out to you too. And I also thank Mr. Sandeep Nayak and Mr. Rohit Johnson, the technical maestros behind today's session. How can we forget all our participants who have joined us from various parts of our country today? But for your presence, this endeavor would have been futile. Thank you for joining us today. Hope you had a fruitful time with us here. Thank you. Thank you once again. Have a good day.
And good night. Thank you. There is an announcement. Next Tuesday, there will be a lecture by the Professor Atikur from Jamia Millia Islamia. And he will be speaking on environmental disaster issues and concerns, a global perspective, at the same time, 10 o'clock. And thank you, Dr. Mutulu, for being so generous to share further knowledge. I will be in touch with you, and we will use your expertise in the future. And before we all sign off, we must also thank all our family members who stay muted for so long. And a special thank you to our principal for giving us so much of extra time. Thank you very much. I think.
Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, ma'am.
And good night to you.
Good night, Dr. Mutulu. I'm
Good
sure
day
he,
to you. Good day. It is 12:15 here a.m.
okay, it's about 11:45 in the day over here.
Yes.
Okay. Okay, it was a pleasure.
Yes, sir, sure.
Yeah.
Thank you. I request the host to please end the session. Sandeep, sir, the session can be ended now. So you can leave manually.
Yeah, I think we can.
Sure.
Leave.
Yeah, no,